Getting a late start, but we're gonna start a review for the final exam, and I think let me check my. Let's see. There we go. Okay, I think it's going to take more than one session, so I'm gonna label this one part one. And that's not an issue. Means everybody's going to take their exam in Brightspace. But the review document that we're working from is actually compiled from a whole host of questions that have been given to you throughout the semester. And you can see what it looks like there. That's the key that I'm going to work from. This is the document that you should find in Brightspace. And then if you need worked problems, I also have those. Every one of these problems is worked out in my handwriting. So I'm only going to cover the ones that are highlighted. A lot of them are highlighted at the beginning, but when we start to get repetition, then I'll pass over those and go to new stuff. All right. So let's get started with question number one. Water has a density of 1 gram per milliliter. That's pretty close. That's close enough to answer this question. Which of these objects will float in water? All right, so we've got objects 1, 2, and 3. And the rule is the density of the object, if the density of the object is greater than the density of the fluid, that is in this case water, and if it's greater than 1, then it will sink. If it's less than 1, it'll float. So less density means float. So if we look at the masses here, mass and volume, and we know that density equals mass divided by volume, and we're given 50, 60.9, 50, 60.9, and 100 grams. Right? And the volume for each one is 69.4, and followed by 54.7 and 40 milliliters. So if we divide the mass by milliliter, we'll get grams per milliliter, which is in the same units as the density of water. That's what we want. We want to compare apples and apples. But we don't have to go in and calculate every one right down to the first decimal point. All we need to know is which one of these is less than 1, right? That means it will float. So if we divide 50 by 69, that should give us a value that's less than 1, right? If the denominator is greater than the numerator, then this will be less than 1. Denominator divided by numerator greater than 1. Denominator divided by numerator greater than 1. So this is the only one that's less than 1. It's the only one that will float. That's why B is the answer to this problem. Okay. All right, 2. Which of the following describes a chemical property of gold? Property. Property refers to potential instead of change. Change means that you actually observe a difference. Now, if it's a physical property, then we're describing only the potential to maintain the identity of the substance. Anything that happens to that substance will not change its identity. That's referencing the property. Anything that speaks to the potential of changing the identity of the substance is a chemical property. So if we look at our choices here, A through E, gold is very dense, right? Density says nothing about the identity of the substance. It just says mass divided by volume. B is gold is a soft metal. That's an expression of a physical property. In other words, we could probably scratch it with our fingernail. That didn't change the identity at all. Gold is inert, non-reactive. There's the key. Inert, non-reactive. That's talking about the ability of gold to undergo a chemical change. In other words, a change in identity. If gold reacted with some element like chlorine and made gold chloride, that would produce a different substance. So C is a chemical property expression. And the others should be physical. Gold is yellow, that's just a color. Gold is a good conductor of heat and electricity, that's just a physical property too. There's no change in identity under those circumstances. Right? So C is the only answer that's possible here. All right, number 3. How many significant figures? Significant figures in this number. Right? Yeah. 1, 2, 3, is that right? Yep, and then there. So what are the rules for significant figure? Well, the first rule is all non-zero numbers are significant. That one is significant. All right. Zero numbers come in 3 flavors. There are zeros to the left of the non-zero numbers, right? We don't have any here, so we don't have to worry about that. Zeros to the right are only significant if there is an explicit decimal point. And there you have it right there. So all of these zeros are significant. Right? So that's 1, 2, 3, 4, 5. 5 significant figures in that number. How about this one? Number 4. Let's see, we have 004 0090. 004 0090. Okay? So that one's significant. That one's significant. Zeros between non-zero numbers are significant. So these are significant also. How about these two? Zeros to the left of non-zero numbers are not significant. But zeros to the right are only significant if there is an explicit decimal point. There it is. So that one is also significant. So we have 1, 2, 3, 4, 5 in this one also. 5 significant figures. And I'd like to emphasize the point. That's the correct way to write a decimal number, right? With zeros, with nothing to the left of there are no non-zero values to the left of the decimal point. So you bracket it by a 0. If you do this, that is wrong. And every time I see that on a paper from a student, I count it wrong. That's what I call an orphaned decimal. This one needs both parents on both sides. All right. Let's see, number 5. Which is an example of a homogeneous mixture. All right, a homogeneous mixture. Remember, a mixture is a combination of 2 or more pure substances. In other words, a pure substance cannot be reduced any further by physical means. It cannot be separated into different pure substances. So once you mix those pure substances together, then we are interested in what do those substances do? Do they mix uniformly throughout to where you have an equal concentration of each in any sample that you take? That's a homogeneous mixture. Heterogeneous mixture means you have different composition everywhere in that mixture. So we're looking for a homogeneous mixture, right? Let's do it by process of elimination. A, soil or dust. That is heterogeneous in terms of at least particle size, but usually it's also heterogeneous in terms of chemistry. But this one is hetero, right? So that's not it. Sodium chloride. Sodium chloride is a compound, but that is a pure substance. Okay, it's not a mixture. Aluminum. Aluminum is also a pure substance. It's an element, right? Not a mixture. Vodka. Vodka is a homogeneous mixture of water and ethanol and other stuff. Not much other stuff, but water and alcohol. So this one is homogeneous. And the last one, oily water, has to be hetero. Because water and oil don't mix, right? No matter how hard you shake it, within seconds after you stop shaking, the oil will float to the top. So we found our homogeneous mixture. All right, number 6. Okay, a cat is 7.1 pounds. What's the mass of the cat in kilograms? All right, this is just unit conversion, right? Dimensional analysis. 7.1 pounds. And it doesn't matter if it's cat or not. We're only interested in the mass. So 7.1 pounds, actually, 7.1 pounds is a measure of force. It's not mass. In the imperial system, the measure of mass is called a slug, but we didn't deal with that. What we're trying to equate is 7.1 pounds to mass in kilograms, and we can do that as long as we're on the surface of the earth. Then this relationship, 1 kilogram is 2.2046 pounds, that will hold. But it only works if you're on the surface of the earth under 1g gravity acceleration. So what type of conversion factor do we need to give us kilograms? Well, that needs to be on the top. This needs to be on the bottom so that we can cancel, right? So the relationship here, this factor is kilograms and pounds, 2.2046. There and there. Then we can do the calculation. And I'm going to do the calculation because I want to introduce one more topic along with it. So 7.1, 2.2046 divided. My calculator says 3.220539. Okay. Is that the number I report? No. Because we've got significant figure rules. This is a multiply rule, right? So when we multiply, we're limited to the fewest number of significant figures in the starting number. And that's this one, 2 significant figures. Now this one is an exact number. All conversion factors are exact. In other words, they have no impact on the outcome except the calculation itself. So we're limited to 2 significant figures. So I would call it there right? Since that's 2, I keep the 2. The answer is 3.2 kilograms. All right, let's skip down to number 8. Which of these is a chemical property? All right, now we're looking at the potential for change in identity. Ice melts at 0 degrees. B, C, D, and E. This is physical, right? Water has a high specific heat. There's no implication as to the change in identity of water. It's just the specific heat of water. That's a physical property. How about sodium is a soft, shiny metal, right? It's like the gold was before. Gold is soft. That's a physical property. Helium is very non-reactive. That is a chemical property. Helium is non-reactive. Glycerol is a viscous liquid. That's physical. Okay. So there's our answer. All right, number 10. Uh, 485.5 K. 485.5 K. Which means what? This is an expression of temperature in the Kelvin scale. And our choices are in centigrade or Celsius and Fahrenheit. So in order to go to Fahrenheit, we need Celsius. So let's go to Celsius first. Right? So we need to subtract 273 from that. Right? That's 212 degrees C. Right? Why did I know that? Because K equals C plus 273. So 273 subtracted from K equals C. Now, do we have one of those? Is that one of the answers? Let's see. Yeah, D. Right, we found our answer. We didn't even have to go to Fahrenheit. Right? If we did need to go to Fahrenheit, what would we do? Well, we'd look in the useful information and find the formula. Right? Fahrenheit temperature equals 9/5 times C plus 32. That's the way I memorized it. Sometimes you'll see this as 1.8 instead of 9/5. Same thing. Okay, we didn't need that this time though. All we needed was the conversion from Kelvin to Celsius. Let's see, how about 14? Which of the following is only a physical change? Now we're talking actual, change, like going from one place to another place. And if it's a physical change, there's no change in identity of the substance. Chemical changes will be a change in identity. So, what are our choices? A says leaves turn colors in the fall. The leaves turn colors, why? Well, because part of the leaf is the chlorophyll is being removed from the leaf. And what's left over are the colored compounds that are masked over by the chlorophyll during the rest of the season. So the reason they turn colors is because of a chemical change. It's a biochemical process, right? So this is a chemical change that we're witnessing. The problem with A is you might focus on color and think that color is only physical. Well, what caused the color? Chemical change caused the color. The indication of the color is from a chemical change. Banana ripens. Right? Banana ripens because of other biochemical changes in the fruit. Right? Cookies burn in the oven. Right? We're carbonizing them. Right? That's chemical change. It's not a cookie anymore if you burn it. Right? It's just carbon. Sugar dissolves in coffee. We're making a solution here with sugar as a pure substance, and coffee is a homogeneous mixture at this point, but we're adding another component and adding a pure substance to our homogeneous mixture, and it's still homogeneous. But we didn't change anybody's identity. Sugar is still sugar, coffee is still coffee. That's a physical change. And the last one should also be chemical. Well, let's see. At least two of the above exhibit physical. No. This is the only physical change in that group. All right. Number 16. If a 100-gram sample of metal has a volume of 8.65 milliliters, what's the density? All right, this is very simple. Okay. Density equals mass divided by volume. Now, the units of measure, what about our answers? Our answers are in grams per milliliter. The mass is 100 grams. 100 grams. All right, that decimal means those zeros are significant. Right, we have three significant figures here. And the volume is 8.65 milliliters. Right? And remember, whenever you do a calculation with a number and its units, you do the same thing to the units that you do to the numbers. We're dividing 8.65 into 100. Here we're dividing milliliters into grams. Right? They can't cancel because they're different units. So we have to retain them as grams per milliliter. Right? Grams divided by milliliters. And then 8.65 into 100. My calculator says 11.5607. How many of those can I keep? Well, you got three significant figures here, three there. This is a multiply divide rule. So you just go to the least significant numbers. Both of them have three, so we're going to draw the line there. That means 11.6 because this one is greater than 5 grams per milliliter. Okay, that's why the answer is D. All right, 17. The number 14.809 rounded to three significant figures. All right, 14.809. Let's assume, say, you get that number as an answer to a calculation. Right, your calculator says 14.809. We want to round it off to three significant figures. Start from the right and move over until you get three significance right here. Then you look to this one, that's less than 5. So we keep that one and throw these away. So our answer is 14.8. 18. Which of the following is an incorrect description? All right, which ones don't match? All right, I need more room than that. So let's do this, 18. And then we have these choices. Okay, A choice, homogeneous mixture. Which of the following is incorrect? So A is correct. That's fine. A solid element. Oh yeah, most of the elements in the periodic table are solid. Okay, how about C? A solution of gases. Yeah, homogeneous mixture of gases is a solution of gases. And whenever you mix two or more gases together, they always form a homogeneous mixture, right? There are no exceptions because as long as there's no chemical reaction, right, then you mix them together, they form a mixture because there's a lot of space between the molecules. There's plenty of room for everybody, right? So that one's true. How about D, a mixture of solids? Can you get a mixture of, oh yeah. You may have to melt them first before they're solid, but yeah, you can get them like brass, right? Brass is um, nickel and copper. Or let's see, sometimes, uh, no, copper and tin is bronze, right? Bronze equals copper and tin. But sometimes they put something else in here, copper and I forget what it is, but that's one type of brass. How about E? 18E, a heterogeneous compound. No, compounds are not mixtures. So that one's wrong, and that's the answer. Those two terms do not go together. How about 20? Yeah, we're doing on time. Coming up on 10 o'clock. All right, we're good. Twenty. The state of matter for an object that has neither definite shape nor definite volume. All right, so we're talking about solids, liquids, or gases, right? And we can characterize them by both their shape and their volume. Okay, solids have a definite shape and a definite volume. Liquids have an indefinite shape, but a definite volume. And gases have an indefinite shape and an indefinite volume. So if we're saying it has neither definite shape nor definite volume, we're talking about a gas, and that's D. Okay, we've got some repetition. We're skipping down to 24. Now, just because we skip problems doesn't mean they aren't useful, right? They give you practice. But I'm trying to stick to unique questions. There may still be some repetition. How many of the following are pure compounds? Pure compounds. That's redundant. A compound is pure by definition, right? Well, sodium is an element, right? That's not a compound. Sugar, yeah, sugar is a disaccharide. That is a compound, right? So we got one, right? That's sugar. Oxygen is an element. It's a diatomic element, right? Two oxygen atoms bound together, but it's not a compound. Air is a mixture, right? Iron is an element. So there's only one in there that's a compound. That's sugar, right? It's C12H22O12. That's sucrose. And I'm assuming that when they say sugar, that we're talking about sucrose. All right, number 26. Which of the following is a chemical change? Chemical change. All right, we're changing identity. For the process that occurs, we are tracking a change in identity of the substance. Right? How about A? Sugar dissolves in water. No, it's still sugar, it's still water. How do we know? Because all you have to do is evaporate the water and you get your sugar back. Right? So this is a physical change. B, gasoline evaporating. It just goes from a liquid to a gas. That's a physical change. There's no change in identity. Water boiling, similarly, liquid to gas. Right? Paper burning. There it is. Paper. Primarily cellulose, but some other things. And it's being converted by combination with oxygen in the air. It's making carbon dioxide and water, and some uncombusted, usually, carbon left behind, depending on the paper. There's some papers that go, and there's nothing left. Butter melting, no, that's physical. There's your answer right there. Uh, 28. Right. What's the most abundant element on the Earth, including the crust, the oceans, and the atmospheres? Well, think about the various, the crust, the oceans, the atmosphere. The atmosphere is 21% oxygen. That's a lot of oxygen, right? Most abundant element. Now, are we talking about the most abundant element by mass or by numbers? I think the implication here is mass. And oxygen weighs more than nitrogen. And if we're combining all three of them, now nitrogen is more abundant here, is more abundant there. But if we combine the atmosphere and the oceans and the crust all together, then you're talking about oxygen. So this is oxygen for the atmosphere. How about oceans? What are oceans made of? Mostly, there you go. So definitely oceans are mostly oxygen. And the crust is mostly silicon and aluminum and some others, but they're all combined with oxygen, right? So that combination with oxygen for all of the metals and nonmetals in the crust means that oxygen overall is the most abundant element by mass. All right. Let's see. Correct name for FeO. All right, here comes your nomenclature. Can you name compounds? All right. First of all, type 1, type 2, type 3. If it's a type 1 or 2, the first element is a metal. Yep. So it's either a 1 or a 2. It's not a 3 because that's two nonmetals. So now we have to decide which one of these it is. Well, if it's type 1, it has fixed charge, right? Fixed charge for the metal. This one is variable charge. All right. Most of the variable charge elements are transition elements. Now, there are some in the representative side of the table that have multiple charges. And there's some in the transitions who have fixed charges, which would put them in this group. Let's see, those three of those are copper, silver, and cadmium. They have fixed charges. Like, no, it's silver, cadmium, and zinc, excuse me. Silver, cadmium, and zinc. Copper can be a 1 or a 2. All right. Silver's a 1, cadmium's a 2, and zinc is a 2. 2+ charge. All right. So those are fixed charges. They would be here. But iron is variable charge, right? It can either be a +2 or a +3. Right? In this case, what is it? Well, how do you determine that? You look at the anion, oxygen. Oxygen is in a position in the periodic table where if it's in an ionic compound, it's always a -2 charge. Right? It's a chalcogen, and all the chalcogens are -2s when they're in ionic compounds, when they're combined with metals. Right? So that's 2 minus. This has to be a 2+. So now we can name it. Right? We just say iron, and then we have to say what the charge is with a Roman numeral, and then we say oxide. Add the IDE ending. Iron 2 oxide is the correct name for this compound. All right, 32. When the following equation is balanced using the smallest possible integers, what is the number in front of the substance in bold type? What's the coefficient for iron? All right, so we're starting off with aluminum and then Fe3O4, Fe3O4, and it's making Al2O3 and iron. Let's see, let's give ourselves some more room here. There we go. Okay, so how do we do the budget method? The budget method, remember, we take all our elements and put them down this side. Aluminum, iron, oxygen. Then we do an initial tally. 1 aluminum, 3 iron, 4 oxygen. And then on this side, we have 2 aluminum, we have 1 iron, and we have 3 oxygens. Okay. Then we go to, one of our tricks, our useful hints, is that if you have these elements, you don't touch them right till the end. So what we want to do is balance the oxygens. Right? How do you balance an oxygen if it's only in one place here, one place there, and we can't use a simple multiplier to get one side equal to the other? Then cross multiplication can work. That's another trick, right? If we take 3 here and 4 there, then what do we get? Well, we get 12 oxygens and 12 oxygens. But we have to recalculate our iron and aluminum, right? So that's 9 irons and aluminum is 8. Okay? That's not right. Aluminum is 8. There we go. And 9 irons. Okay, so now that we've got the oxygens balanced, we can balance the aluminum and the iron on either side with coefficients. We've got 9 irons here. We need 9 irons there. And we have 8 aluminums on this side. We need 8 here. So now it's balanced. The coefficient in front of the iron is 9. Okay, so I used 2 hints, 2 tricks. One is hold these out till last, right? Why? Because the coefficient in front of this one changes only that one. It doesn't change anything else. So keep it till last. And then if you have an element on one side, element on the other side, only one location, and you can't reconcile the numbers by a simple multiplier, then cross multiply. 3 over here, 4 over there. That gives you the same number of oxygens on both sides. Then you can go from there. Number 33. And these steps, I've said it before, these steps in balancing equations are not taught in most textbooks. At least they weren't when I was going to school. I think some of them are catching up now. But these procedures are not commonly taught to the beginning chemistry students. A gas occupies 30.3 liters at 2 atmospheres and 27 degrees. How many moles of gas are present in the sample? All right, let's see what we're given. Volume is 30.3 liters. Okay. Pressure is 2 atmospheres, and temperature is 27 degrees. See? And the question is, how many moles? What does that remind you of? That reminds you of one of the gas laws. In fact, not the combined law, because this is not before and after. We're not given conditions before and then a change. We're given state conditions. What is it right now? Which means you want to use the ideal gas equation. Like that. So we want to solve for N. N equals PV on RT. Okay, but we need the correct units. If R is going to be 0.08206 liter atmosphere per mole K, that means the temperature, the volume has to be liters, pressure atmospheres, temperature has to be Kelvin. All right, so that's 300. So now we would put 300 here. And pressure then would be 2 atmospheres. And volume would be 30.3 liters. Okay. Now, if you want to check to be sure everything is kosher, say, all right, this is in the denominator, numerator, cancels. Numerator, denominator, cancels. Denominator, numerator, relative to one another, cancels. This is moles. The denominator of the denominator is the numerator. It flips. So that gives you moles of gas. Now all we have to do is crunch the numbers. So 2 times 30.3 divided by 0.8206 and divided by 300 gives you 2.461613. That's according to my calculator. All right, how many of these can I keep? Well, let's see. We've got 3 there, 3 there. That doesn't count. And 3 there. So we're limited to right there. This is 2.46 moles of gas. Okay? All right. Let's see. Oh, okay. So we can move to 34. 34. You're holding 4 balloons. Each contains 6 grams of a different gas. All right. The balloon containing which gas is the larger? Right. If they've each got 6, right? These, I'm not drawing them to scale. Like one of them is going to be larger than the other. I'm just saying that each one has 6 grams of gas in it. Okay, so we have to assume that the temperatures are all the same, right? Temperatures are equal, pressures equal, masses are equal, volume is the question. Now, how does the volume vary if these two are constant? Temperature, pressure, it varies with the number of moles. These two vary. Divide those two, that's a constant. So what we're saying is the one that's the biggest volume, the largest one, has the greatest number of moles. All right, greatest number of particles. So if they're all the same mass, which one would have the most particles? Right? Each particle has its own mass. And to get to 6 grams, you need so many of those particles. Right? So if the particle is the lightest one, to get to 6 grams, you need more of the particles. So the one with the greatest number of moles is the gas that has the smallest mass per particle. All right. So if we're looking at these gases, let's see. Well, E says all the same. We know that one's not going to be true. But we have nitrogen, helium, krypton, nitrogen, helium, krypton, and neon. All right, let's look at the molar masses here. Nitrogen is about 28. We don't have to be exact because they're significantly different from each other, right? This is 2 times 14. Helium is about 4. Krypton is about 84. And neon is about 20. So the lightest one is going to have the lightest one per particle. We'll have to produce more particles to have the same mass. So the lightest one here is helium. That will have the greatest number of particles and consequently the largest volume. All right, number 38. Zinc metal is added to hydrochloric acid to generate hydrogen gas and is collected over a liquid whose vapor pressure is the same as that of pure water at 20 degrees, 18 torr. The volume of the mixture is 1.7 liters and its total pressure is 0.508 atmospheres. What's the partial pressure of the hydrogen gas in this mixture? All right, let's draw a picture. All right, so we're collecting hydrogen gas from a reaction. Let's say we have a vessel here, and we're taking the gas, and it's being delivered to, let's say, a vessel like this, and it's being delivered to a measuring device, say a graduated cylinder, and we got bubbles of gas going up here like that. It's collecting at the top. Okay. All right. This is water at 20 degrees. Okay. We're also given the vapor pressure at this temperature. Pressure of the water is 18 torr. Okay. All right. I'm not going to put the reaction over there because it doesn't matter. we're only interested in the hydrogen gas. So this is hydrogen gas plus water vapor. Both of them are there together. Now, the total pressure is 0.508 atmospheres. 0.508 atmospheres. 0.508 atmospheres equals total pressure. We're working in torr, so we need to convert that to torr first. Right? Atmosphere, 1 atmosphere is 760 torr. Let's do that calculation first. 760 times 0.508 is 386. 386 torr. That's the total pressure. Okay? So, Dalton's law of partial pressures says that the total pressure, in this case, I'm going to be specific. The total pressure in this region up here is equal to the pressure of hydrogen gas plus the pressure of water vapor. Okay? Now, why didn't I put the volume up here? Because it's irrelevant. We don't need to know the volume to answer this question. We just need to know what's the total pressure equal to, there's the question, and here's the pressure due to water. Okay? So the pressure of H2, oops, not water, pressure of H2 equals 386 minus 18. 368, right? 368 torr is the pressure of hydrogen. Okay? So, this is a word problem, right? Word problems are designed to confuse. They give you information that you need, most of it. Sometimes you have to go outside and look for something like molar mass, things like that. But they very often give you information that you don't need to answer the question. So what you have to do is have a clear idea of what the question is and what the answer needs to be. Then you can ignore the stuff that you don't need and answer the question in the process. That's why drawing a picture helps a lot. Okay, 39. Okay, solid carbon dioxide is placed in a Ziploc bag. See, solid carbon dioxide sublimes, it turns directly from solid to gas. Yep, that's true. At a rate of 0.726 grams per minute. So the rate of sublimation equals 0.726 grams per minute. Okay. If the pressure builds to 3.75 atmospheres, so the final pressure after sublimation is complete is 3.75 atmospheres. Okay. And the temperature is 21.1 degrees. 21.1 degrees C. All right, we may not need all this, but I'm going to put it up here anyway. What's the final volume of the bag after 4.97 minutes? Okay, time, elapsed time equals 4.97 minutes. 4.97 minutes. Okay. And assume that the solid carbon dioxide left over in the bag is negligible. All right, so we're looking for the volume of that bag. All right, How can we find that? Well, we've got pressure, we've got temperature. If we want to find volume, we need moles, right? And then we can use the ideal gas equation. We can use this one. And we want to solve for volume. So moles is what we're missing. All right. If we know it goes this fast for this amount of time, right? 0.726 grams per minute, right? Notice that minutes cancel. And this gives us grams of carbon dioxide. Right, that's 3.608 grams of CO2. Now we can convert that into moles, right? All we need is molar mass. So what's the molar mass of carbon dioxide? Well, let's see, carbon is 12.01 and 2 oxygens is 32. So that's 44.01 gram per mole. Let's stick it over here so I don't get in the way. Put that answer here. 44.01. And that's 8.199. That's good enough. Times 10 to the minus 2 moles. Okay, now we can fill this out. Number of moles, 8.199 times 10 to the minus 2. I'm going to leave the units out here so we can, because of space limitations. R is 0.08206. Temperature, what's temperature? Uh-oh. We got to add 273 to that because temperature has to be in Kelvin, right? 294.1. Okay, and then volume. Well, the volume's there. Wait a minute, that's not right. Pressure, excuse me. Pressure is 3.75. Okay, now we can do our calculation. I've already got that one in my calculator, so I just multiply by 0.08206 and 294.1 and divide by 3.75. And I get volume equals 0.527639 liters. Our answer is in liters or milliliters? Milliliters. All right, let's get our significant figures first. All right. We had, we're limited to 3 here, 3 here. Yeah, 3 here. So we're limited to 3. So it's that one right there. This volume equals 0.528 liters, which is 528 milliliters. All right, remember, when the units get smaller, the number gets bigger. So that tells you which way to move the decimal. 1,000 milliliters in liters, that means 3 places. 1, 2, 3. 528 milliliters. Okay? Solve that problem. Number 41. We're doing on time. Okay, we're good. You're holding 2 balloons of the same volume. Okay. So there's a balloon. And there's a balloon. Volume 1 equals volume 2. Okay. One balloon contains 1.05 grams of helium. Grams of helium. Okay. The other balloon contains neon. And we're not told the grams there. What's the mass of neon in the balloon? Okay. if they are exactly the same volume, and we also have to assume that their temperatures are the same, right? And their pressures are the same, right? We're not told that, but if we don't know that, we can't solve the problem. In that case, we know that the moles of helium equals the moles of neon. Okay? All right. So 1.05 grams of helium. How many moles is that? 1.05 grams of helium. Convert that to moles. Right? And helium is 4.00, 2 decimal places. Right? So I want to do this in individual steps. I could put it all together in one calculation, but that might mess with your heads. We need to know how many moles of helium it is because that's the same number of moles as neon. All right. All right. 1.05 divided by 4 is 2.63 times 10 to the minus 1 moles. And that's helium. It's also neon. Now, if we know that many moles of neon, then we can convert that back to mass. Right? This is moles, excuse me. Moles, grams. So neon is 20.18 times this value. And that's 5.30 rounded to 2 decimal places. So 5.30 grams is, well, the closest one is 5.29. There's a rounding error in there. All right. So I could have put that into one equation, but I think this way is less confusing. 44. All right, a gas occupies 42.6 liters at 2 atmospheres and 27 degrees. Calculate the volume if the pressure is decreased to 1 atmosphere at constant temperature. Okay, so what type of problem is this for gases? It's a before and after. We're given conditions before, and we're changing one of those parameters. We're changing the pressure. Temperature doesn't change, so we don't have to worry about that one. But we do have an initial volume equal to 42.6 liters. Initial, not temperature, initial pressure of 2 atmospheres. And we want a final volume that we don't know. But the final pressure we know is going to be 1 atmosphere. Okay? So when we have pressure and volume involved, before and after, we're talking about Boyle's law. Right? And the equation we use is the before and after version. PI/VI equals PF/VF. Right? Before and after. We're looking for this one right here. So we would say this is PI/VI divided by PF. Right, now we can put in our values. Initial is 2 atmospheres. Initial volume is 42 point, get my decimal in the right place, 42.6 liters. And then the final is 1 atmosphere. So we're actually doubling that value. So that'd be 85.2, right? Liters. Answers in liters? Yeah, 85.2. Okay. You notice a bunch of different answers in multiple choice. At least one of those answers is derived from putting 1 up here and 2 down here. So we would take half of 42 and a half will be 21.3. C. If you put these in the wrong places, then you'll get 21.3 and you say, oh, there it is. That must be the answer. No, it's not. It's wrong because you calculated it wrong. That's the way multiple choice questions are structured so that the creator considers possible mistakes that a student might make. That's one of the mistakes, puts that answer in there. So if you don't know what you're doing, you're going to get an answer that's there, but it's the wrong answer. That's why extracting information from a word problem, putting it on the board in a table can be very helpful because you put the values in the proper position, then you can use the correct formula. All right, 45. You have a partially filled party balloon, 2 grams of helium. You then add 3 grams of hydrogen. Assume constant temperature and pressure, okay? How many times bigger is the party balloon? Comparing before and after the hydrogen gas has been added. Choose the best formula to use to solve this problem. Okay, so we're not actually going to calculate it. We're going to use the best formula. All right, so we've got 2 grams of helium, right? Mass of helium equals 2 grams. And the mass of hydrogen, is it? Yeah, hydrogen. Mass of hydrogen equals 3 grams. Okay. So you're going to have a before volume here. Initial volume is going to be something. And then when you add this one together, then you're going to produce a new volume. Okay. So what do we know about this one? Well, we know the molar mass so that we can derive the moles, right? The moles of before, right? The initial moles before. And then we can derive the moles here, moles of hydrogen, and then plus the moles of helium gives us a new NF. That gives us a new mole. What's the relationship between moles and volume? As the moles increase, the volumes increase. So if we have an initial volume here with that many moles, and now we're going to change to a final volume with a final number of moles, right? Then we can actually say this is 1 and this is 2. That works. Well, which one of these works? Well, D might work if we do it right. If this is 2 and that's 1, and that one has 2 on top, then we move this one over here. So this is V2 over V1. What does that mean here? That means this one comes over here, N1 over N2. Well, that didn't work. All right. That didn't work at all. Wasn't what I expected. Let's see where I went wrong. number 45. I may have had used the wrong approach. Oh, okay. All right, let's take a different approach. If we know we're comparing, we can't compare masses, right? And with the gas laws, it just doesn't work. So we can find out the number of moles to begin with. The number of moles to begin with is proportional to, let's see, this is proportional to the volume to begin with. And then we know the moles after is proportional to the volume after. So they're directly proportional. As the moles increase, the volume increases. So if we have a final volume and an initial volume, then we should be able to relate this volume to this number of moles, and that volume to the original number of moles. Right? And especially since we want to find out what the volume is, right? We have to have an equation with volume in it. Temperature didn't change, so A can't be it. Pressure didn't change, so B can't be it. The ratio of masses doesn't work for gases. It's the number of particles, so C doesn't work. And pressure and volume are the same, so E doesn't work. So by process of elimination, D can only be, that's the only possible answer. Right? You can solve it two different ways. Hopefully you solve it by knowing the gas laws. But test-taking technique can solve it for you also. A gas occupies 18.5 liters at standard temperature and pressure. What volume will it occupy at 735 torr and 57 degrees C? All right, we know a before condition and we're given an after condition. So let's see what the before condition is. A gas occupies 18.5 liters. So that's the initial volume, 18.5 liters. At what temperature? Initial temperature is, this is a gas. That's 0 degrees C. Plus 273 equals 273 K. And standard pressure equals 1 atmosphere or 760 torr. Okay? Now, we're going to change and we want to know the final volume. Did we change the temperature? Yeah, and now it's 57 degrees. Final temperature is 57 plus 273, which is equal to 0.33. Okay. And pressure changed to 735. Pressure 735. Okay. What situation do we have now? We don't have an individual gas law that works. What we need is the combined gas law. So the combined gas law is initial pressure, initial volume, initial temperature, and initial moles. Final. Okay, moles didn't change, right? So we can throw that one out. We don't need moles. It didn't change at all. But we do want to find out what the final volume is. This one right here. So the final volume then is equal to PI/VI/TF and TI/PF. There we go. So what's the initial pressure? 1 atmosphere, 760 torr. Initial volume, 18.5 liters. And final temperature, 330 K. Then initial temperature is 273. And final pressure is 735 torr. That's the thinking part. Now we just crunch some numbers. And I get 23.1 liter. Okay. 46. Doing a lot of gases, it looks like. They are important. How about acids and bases? 48. Identify the Bronsted acids and bases in the following equation. All right. HSO3 minus plus CN minus yields HCN and SO3 2 minus. Okay. Which is the acid? Well, that can't be an acid, Lowry-Bronsted, because it doesn't have a proton. It doesn't have a hydrogen, right? So this one has to be the acid. So if this one loses its acid, what's it look like now? Well, it looks like this one, right? The proton leaves with a positive charge and its electrons stay behind, which increases this one by 1 negative value. So this is the conjugate base of that acid. That means this is the base and this is the conjugate acid of that base. So AB should be the correct arrangement. 49. All right, which has the highest hydrogen ion concentration? 0.4 molar rubidium hydroxide or 0.2 molar calcium hydroxide. All right, 0.4 molar rubidium hydroxide. These are both strong bases, strong bases. 0.40 molar rubidium hydroxide, right? Yeah. Rubidium is an alkali metal, so it only has one hydroxyl. This is a +1, that's a -1. And then 0.20 molar calcium hydroxide. Oops. There. Okay. So if we're looking for a hydrogen ion concentration, we want to see what is the concentration of hydroxyls here, right? Because that relates it to the concentration of hydrogen ions. Remember, in any aqueous solution, this times this equals 1 times 10 to the -14. Let's see, that's not molar. It's just 1 times 10 to the -14. Okay, so this is constant. So if we have a difference in hydroxide ion concentration, then we'll have a difference in hydrogen ion concentration. So this one is 0.40 molar hydroxide. Right? This one is 0.2 molar, but there are two of them. So this is 2 times 0.2 molar equals 0.40 molar hydroxide. So the hydroxide ion concentrations are exactly the same, which means the hydrogen ion concentrations are also equal. D. Right. Hydrogen ion concentration is equal for both of them. So that's D. Number 50. Calculate the pH of an acid solution containing 0.044 molar HNO3. Right? If we're going to calculate the pH, we have to know what the hydrogen ion concentration is, right? Because pH equals the negative log of hydrogen ion concentration. So, do we have enough information? Yeah, that's a strong acid, right? With only one hydrogen per molecule. If it's this molarity for the molecule, it's that molarity for hydrogen ion concentration. Okay. So we can say negative log of 0.044 molar. And let's see. We have two significant figures, that means 2 decimal places in our answer, 1.36 pH. Okay? All right. 51 is next. Which of the following statements is or are correct? All right, let's do it this way. A, D, and E. All right, first question. First statement. In a neutral solution, hydrogen ions equals hydroxide ions. That is true. Okay. In acidic solution, hydrogen ions concentration exceeds hydroxide ion concentration. That is also true. C says in a basic solution, hydroxides exceed hydrogen ions. That's also true. D says all the above statements are correct. That is also true. And this one says none of them are. Right? So D is your answer. All right. 51, 52. Yep, 52. Calculate the hydrogen ion concentration in a solution with a pH of 5.15. All right, if a pH is equal to 5.15, what does that mean? That means it's the negative log of hydrogen ion concentrations. So you have to know what log means. Base 10, right? We can't use that negative there. That negative's got to be gone. So we put the negative over here. Now we can deal with the anti-log. What this means is this value is the power of 10. That equals this value. That's the definition of a logarithm. So 10 to the minus 5.15 is 7.07945 times 10 to the minus 6. Okay. So how many of those can we keep? Well, there are 2 decimal places in this logarithm. That means 2 significant figures are allowed. we can only keep these two. So this is 7.1 times 10 to the minus 6 molar hydrogen ion concentration. Okay. All right. 53. Yeah, it was given out. Try this one. A solution where hydrogen ion concentration is 10 to the minus 13 molar is acidic, neutral, basic, or strongly acidic. All right. So if hydrogen ion concentration is equal to 10 to the minus 13, what's the negative log of that value? Negative log of this, negative log of that, right? This is 13. That's pH. Excuse me. pH is 13. That means it's basic and extremely basic. So D is a correct answer. It's not acidic, it's not strongly acidic, it's not neutral. It is basic. All right. Let's skip a few down to 58. At 10 minutes. Choose the pair of compounds with the same empirical formula. Remember what the empirical formula is. Simplest whole number ratio. Okay? So, if our first one is H2O and H2O2, what's the simplest whole number ratio here? That's it. 2 to 1. This one can be reduced to HO. So they're not the same. How about C2H2 and C6H6? This one can be reduced. Divide by 2, we get CH. Divide by 6, we get CH. So that's a good answer. If we look at the others, dipotassium chromate and potassium dichromate, we can't reduce those any further. Right? You can't divide by anything and get them. So they're neither one of them is the same. So that one doesn't work. D says sodium bicarbonate and sodium carbonate, right? One's got hydrogen and the other one doesn't. So that one can't work. And barium carbonate and barium bicarbonate or barium hydrogen carbonate, same thing. One's got hydrogen, the other one doesn't. Can't work. So B is the only possible answer. Or empirical formula. All right, let's scooch down to 60. Okay, acetylene gas is 92.3% carbon, 7.7% hydrogen, and its molar mass is 26 grams per mole. What's its molecular formula? All right, this procedure, you have to be very methodical about it. We want to go first by percent by mass, 92.3% by mass carbon. We want to go from there to moles of carbon and moles of hydrogen so that we can get the empirical formula. Then we can go from the empirical to the molecular formula. So here's how you do it. 92.3% carbon. Hydrogen is 7.7%. And this is mass. Remember what I said about percentages. Percentage is a dimensionless number. You have to know what its origin is. And this percent means 92.3 grams per 100-gram sample. That's what percent means. We can't get moles from that. We need a mass. So we can assume, let's say we have 100-gram sample. Now we have 92.3 grams and 7.7 grams. Now we can go somewhere with this. We can find out the number of moles of each. Carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. Okay. So I do these in steps because each step requires a different action. This is 7.8, excuse me, 7.6685 moles. And this one is 7.624 moles. All right. Now here we come to the part where we have to take into account experimental error, measurement error. Normally what I would do is I would say divide both of them, 7.624, by the smallest value. Right, that equals 1, and this equals very close to 1. So what we're saying is the ratio, the empirical ratio, is 1 carbon to 1 hydrogen. Okay, that's the empirical formula. What we need is the multiplier. Right? The empirical weight is equal to 12.01 plus 1.01, which is equal to 13.02 grams per mole for this formula. But that's not the molar mass. The molar mass is 26 grams per mole. So our multiplier can't be 1, right? 1, no. How about 2? If we do 2, then we get twice this much, right? 2 times that is 26.04 grams per mole. Is that close? Yeah, very close. So if this is 2, then our molecular formula is C2H2. Okay? 61. And that one given out too. Try this one. You have 1 mole of each compound below. Which has the greatest mass? All right. What we need is to be able to write the formula for each one. Sodium hydroxide. Sodium hydroxide is a polyatomic ion with a -1 charge. Sodium is an alkaline metal with a +1 charge. That's its formula. All right, we're going to do the formulas first. Barium carbonate. Barium has a 2+ charge because it's an alkaline earth. And carbonate is a polyatomic ion with a 2- charge. So that's its formula. Iron 3 sulfate. Iron 3+, and sulfate is SO4 with a 2-. So this one has to have a 3 here and a 2 there to balance the charges. D is ammonium nitrate. Ammonium is a polyatomic with a +1 charge. Nitrate's a polyatomic with a -1 charge. That's it. Lead 4 oxide. Lead with a 4+ charge An oxygen with a 2- charge means we need 2 of them to balance. Okay, now we can calculate the molar masses of each one. Right, sodium is 23 and 16 for oxygen and 1.01 for hydrogen. So that's, let's see, 10, that, and that's 10. Yeah, 10. That's 40.1 grams per mole. Barium is a big atom, 137.33. Carbon is 12.01, and 3 times 16 for oxygen, which is 48. I'm going to use my calculator on this one. Which is 206.34 grams per mole. That's pretty big. How about 2 irons? Iron is 5585. 2 times 5585 for iron. 3 times sulfur, which is 3207. And then 12 times oxygen. All right. And 32.07 times 3, and then 16 times 12. So that's 399.91 grams per mole. Ammonium nitrate, we have 2 times 14.01 for the nitrogens. We have 4 times 1.01 for the hydrogens, and 3 times 16 for the oxygens. That's 28.02, and 4.04, and 48. That's 80.06. 80.06 grams per mole. And then lead is 207.21. So this is 207.21 for the lead, and then 2 times 16 for the oxygen. So this is 239.21 grams per mole. If we have 1 mole of each, then we have this mass of each one. And the heaviest one is that one. Okay? Now, if you don't know how to write these compounds, then you cannot answer the question. Okay? That's why I emphasized from the very beginning, learn your symbols, learn how to write the compounds. Right? You've probably figured it out by now. If you didn't do that in the beginning and you're trying to play catch up, it ain't going to happen. Not before the finals. 63. Okay. Let's try one of these to see. A certain compound has an empirical formula of NH2O. NH2O. That's the empirical formula. Its molar mass is between 55 and 65. So the molecular weight is equal to 55 to 65 grams per mole. Okay? What's its molecular formula? Well, its empirical weight is equal to 14.01 for that one, 2.02 for these 2 hydrogens, and 16 for that oxygen. So that's 8, 12, 3203, okay? Grams per mole. We need a multiplier. So what multiplier will put our molecular weight somewhere between there. 1 won't do it. 2 will be about 64. That'll do it. So N2H4O2 will be our molecular formula. Okay, 64. Let's see, I'm going to need a new marker. All right, 64. What's the molar mass of Li2SO4? We're kind of going backwards here. Right? All we need is 2 times lithium, which is pretty light, 694. Sulfur is 3207. And 4 times oxygen. So we add those up. And 32.07 and 264. Which is 109.95 grams. Close enough. B is the best answer out of that one. Rounding errors. Okay, how about 71? Oops, I'm past time. Okay. So I'll have to pick it up here next Thursday. Let me mark my 71 is where we're going to begin. Next one, I'll mark it down. 71. Here it is. This is going to be, let's see, today's the 5th, be 7th. 5, 7, 6. Here we go. So we'll meet back on Thursday, and I'll finish part 2 of this discussion. But for today, we're done.